Have you ever just stopped to think about how life moves so ridiculously fast? I mean, right now, inside you, trillions of chemical reactions are firing off every single second. And the secret agents making it all happen? Enzymes. But here's the thing, these agents work under a very strict contract. So today, we're going to unpack that contract, the two fundamental rules that every enzyme has to obey. It's all about how they balance a reaction's ultimate destiny with the incredible speed it takes to get there.
Okay, so think of a chemical reaction like a journey. You start at point A with your reactants, and you want to get to point B, the products. Now, the overall change in elevation between A and B, that's fixed. An uncatalyzed reaction, that's like trying to hike straight over a huge towering mountain. It's going to take forever. But an enzyme, well, it doesn't magically lower your destination. No, it's way smarter. It's like an engineer that blasts a tunnel right through the mountain. You start in the same place, you end in the same place, but the journey is now millions, even billions of times faster. See? Enzymes are masters of speed, not destiny.
And this idea leads us straight to what we're calling the catalyst's contract. It's basically two unbreakable rules. First, an enzyme must respect the final outcome of the reaction. It can't change the destination. And second, its entire job is to make that journey happen as fast as biologically possible. Let's dig into this contract clause by clause.
So these two parts of the contract, they aren't just made-up rules. They come from two major branches of chemistry, thermodynamics and kinetics. You can think of it like this. Thermodynamics is all about the destiny. It asks the big question, will this reaction even happen on its own? And then you've got kinetics, which is all about the speed. It chimes in and asks, okay, great, but how fast is it going to happen?
This right here visualizes those two questions perfectly. That overall energy drop from start to finish, that's called Gibbs free energy, or delta G. It tells you if the journey is fundamentally downhill and favorable. But then you have that initial hill you've got to climb to get things going. That's the activation energy, delta G star. An enzyme can't touch the overall downhill slope, but that initial hill? Oh yeah, it can shrink that hill down to almost nothing.
So here's the absolute key. A reaction's destiny is completely locked in by its change in free energy, that delta G. If the delta G is negative, like you see on the left, the reaction releases energy and it will happen spontaneously. We call that exergonic. If it's positive, it needs energy put in, so it's endergonic. And because this value only depends on the starting line and the finish line, and enzymes don't change those, they simply cannot, under any circumstances, alter the delta G. And you know, this isn't just a loose concept, it is set in stone by math. The equilibrium constant, KEQ, which basically tells you the final ratio of products to reactants, is directly mathematically tied to that free energy change. As this slide shows with the balancing scale, you literally can't change one without changing the other. Since enzymes have zero power over delta G, they have zero power over KEQ. All they do is help the reaction get to that final balance state way faster.
All right, we've firmly established that enzymes can't change the destination. Clause 1 of the contract is fulfilled. Now for Clause 2, their unbelievable ability to control speed. This right here is where they become superstars.
You see, every single reaction, even one that's totally spontaneous, needs a little push to get going. The molecules involved have to twist and bend into this really unstable, super high energy state. We call it the transition state, before they can relax into being products. And the amount of energy it takes to get to that peak, that's the activation energy. It is the single biggest bottleneck that determines how fast a reaction goes.
And this is the enzyme's masterstroke. Just look at that graph. The gray line is that massive energy mountain for the uncatalyzed reaction. The orange line, that's the brand new superhighway the enzyme builds. By slashing the activation energy, the enzyme makes it exponentially easier for molecules to get over the hump. We're talking reaction rates that are 1 million, 1 billion, even 1 trillion times faster. Then all the while, notice that the overall energy drop, the delta G, stays exactly the same.
I mean, that's just amazing, but it begs a huge question, right? How? How does an enzyme just carve out this easier path? What's the secret sauce behind its incredible power?
Exactly. Where does the energy to pay for this amazing shortcut actually come from? It can't be magic. It has to come from somewhere. And the answer is just one of the most beautiful and elegant ideas in all of biology.
The power source is something called binding energy. It's pretty simple, really. When an enzyme grabs its target molecule, the substrate, it forms a whole bunch of weak little connections, like tiny molecular handshakes, hydrogen bonds, ionic interactions, that kind of thing. Each one is weak on its own, but together forming all those bonds releases a surprising amount of free energy. And that released energy is the currency the enzyme uses to work its magic.
And right here, this is the secret. For a long time, scientists used the lock and key analogy, but it turns out that's a bit wrong. Think about it. If the enzyme lock was a perfect, snug fit for the substrate key, it would bind it so tightly that the reaction would just stop. The real mind-blowing insight is that the enzyme's active site is not a perfect fit for the substrate. Instead, it's a perfect fit for that incredibly unstable transition state, that fleeting, high-energy moment when the key is halfway through turning in the lock.
So check out this transaction. Getting the substrate bent into that awkward transition state costs a lot of energy. That's the big gray arrow pointing up. But, and this is the genius part, when the enzyme binds to and perfectly stabilizes that transition state, it releases a huge amount of binding energy. That's the big blue arrow pointing down. That released energy directly pays for the energy cost, leaving only that tiny little net activation energy to overcome. It's beautiful.
And this slide just brings it all together. The enzyme forges a whole new path, with new valleys, the enzyme substrate and enzyme product complexes, and a much, much lower peak. And that peak is lower precisely because the enzyme uses its binding energy to stabilize that transition state. But look closely. The starting energy of the substrate and the final energy of the product are completely unchanged. The contract is upheld.
Okay, so we've gone deep into the thermodynamics and kinetics, but why does this intricate energy dance matter so much? Well, it's basically the difference between a lifeless puddle of chemicals and, a living, breathing organism. You see, in our bodies, a ton of really essential reactions are actually thermodynamically unfavorable. They're uphill battles. They won't happen on their own. So what do enzymes do? They act like a clever set of gears. They couple that uphill, unfavorable reaction to a massively downhill, super favorable one, like breaking down our cellular energy currency, ATP. The huge energy release from ATP hydrolysis is used to power the smaller, unfavorable reaction, letting us do everything from building muscle to thinking a thought.
And this all leads to a pretty profound point about life itself. A living cell is not at equilibrium. For a cell, equilibrium is death. It's a stagnant puddle. Life, on the other hand, is what we call a dynamic steady state. It's a constantly flowing river of energy and matter. And enzymes, they are the brilliant managers of this flow, directing traffic, speeding things up, and keeping that river moving, maintaining the delicate, energetic state that we call life.
So let's just recap the catalyst's contract with the three big takeaways. Number one, enzymes change the rate, never ever the equilibrium. Number two, the speed of a reaction is all about the height of that activation energy barrier. And number three, the secret weapon, an enzyme's power comes from binding energy, which it uses specifically to stabilize the super unstable transition state, not the starting substrate.
And that leaves us with one final thought to chew on. If enzymes are the ultimate workers on the factory floor, masterfully controlling the speed of production for every single process in our bodies, then what does that make the molecules that tell the enzymes when to work and when to stop? They are the upper management. They are the ones directing the entire economy of the cell. And that, well, that's a whole other story.